was trying to open the door.
Use the door handle.
Do the same thing, but from the other side.
Do the same thing, but the other side.
The inside.
The inside.
So
here.
open.
The side facing you, know what they're trying to say.
Not with your fingers in the hinge. That's just dumb.
It's physics. You're taking something that you've been doing for years and years and years and analyzing what exactly have you been doing.
I mean, usually I just kick it and it works.
All right, so first off, if I'm opening the door, what is the direction of its angular velocity? Abby?
Oh, I don't know.
I thought you just did the hand gesture for it.
It's like this way?
Yeah, that's that thing.
Oh,
So the direction is
down?
down, yes.
Oh,
It's gonna be opening like that. The hinge is vertical, so my thumb's either gonna point down or up. And if I'm doing it that way, that's implying the door is swinging this like that, the door is swinging like that. So it's a downward angular velocity. If it starts at rest, and then starts to swing downwards, that means that the angular acceleration must be downwards, which means the torque must be downwards. So whatever formula I come up with for an individual torque, as opposed to the total torque, let's differentiate that. When I write tau equals I alpha, that's the total torque. But some of the elements that people were telling me is to open it efficiently. Well, let's see. I need to get away from the hinge. So I need to go away from hinge. I need to push perpendicular to what I'm just going to label as R. And there's one other piece that affects how easily the door opens, is how, and I think it was hinted on, how much force I actually apply. So whatever I come up with for a formula for torque, it has to really involve all of this stuff. And fortunately, there is a formula that does this. So if I need to figure out an individual torque, that's the formula.
What is that R? Is that like radius?
This R right here is known as the moment arm.
The moment, what? Arm?
Moment arm, sometimes referred to as a lever arm. It is a vector, thus the symbol, from the axis of rotation to where the force is applied.
So what exactly would be the arm in this case, where the line where the hinges are?
So, if we're looking at an overhead view of the door, I'm going to simplify the hinge there. If I am pushing there, the moment arm is a vector from the axis of rotation to where the force is applied.
The door has 3 hinges. Which hinge?
Well, hopefully they're aligned. So if I'm doing overhead view, they would all be lined up, so it doesn't matter.
So theoretically, where you're pushing it goes like this.
It's from the axis of rotation. So the axis of rotation is a line running straight down there. If I'm pushing there, it'd be the shortest distance from the axis
So
of
it's
rotation.
not each hinge, it's the edge, basically.
It's not, sorry again?
It's not each hinge that's doing the moment arm. It's just the edge of the door. Does that make sense?
Yeah, for a rigid body, you could easily, it is legitimate to simplify it as treated as there's one axis rotation, I just want the shortest.
Okay. And what exactly is it? So just below perpendicular to R, up there?
Force,
This E or O?
that's an E. I put two E's in there, and then I erased, unfortunately, the wrong one.
Can you do a really quick example of finding the moment arm, just the vectors? Like, how is that?
Finding the moment arm, all right, so in this case right here, what's the pivot point?
The middle? Where the hole is?
If it were the middle, then it would have spun backwards, or it would have spun towards the front of the room.
Is it where the rope catches?
Nope.
Is it the outside edge of the wheel?
Where? There's a long outside edge. It's not pivoting around every single point on the edge.
Could it be the edge where the line is on the back?
The edge where the line is on the back. I'm not sure what you mean by that.
That?
Oh. Not in its current orientation.
The point is on the edge that touches the ground.
Yes, the pivot point is there. Since the pivot point is there, when I apply a force this way, I'm applying a force there, there's my force. My moment arm is that vector right there, from the axis of rotation to where the force is applied. Bless you.
Is this cross product or dot product?
It is indeed a cross product. So we need to talk about cross products in more detail than we've probably done before. Looked like you wanted to ask a question.
I was just gonna ask, your drawing, is the wheel the small circle?
No, there's this inner bit and then the outer bit.
Okay.
All right, let's talk about cross products. And at the same time, dot products. When you're multiplying, when you're doing a dot product, what part of the vectors are we multiplying?
What? Say that again?
Outer, like, components?
Okay, so if I have A and B, if I break A up into what we'll call a parallel and a perpendicular. When I do dot products, which two am I what two things am I multiplying?
The I has
Since I haven't defined I hat and J hat.
The parallel, a parallel, perpendicular?
All right, I'm multiplying a parallel and a perpendicular.
No.
If I do A dot B,
AB.
so multiplying that length times that length,
A parallel.
thank you. I multiply the like components, the ones going in the same direction, so the parallel part times B. If I'm doing a cross product, I'm multiplying the perpendicular times B. So the magnitude, so if I do A cross B, the magnitude of that is going to be the A perpendicular times B. Now, dot products is a scalar product, I don't have to worry about direction in the end. But here I do, that's why I have the magnitude of A cross B, because it is a vector product. As one would hope, because, well, over here, I have R cross F, and I give us torque, and there's a vector symbol right there. So, so we're multiplying perpendicular parts. Then, how about the direction though?
K hat.
Well, let's give a situation here. Let's actually define I hat and J hat. I hat, J hat. Which way is K hat? Why?
What's that? Is that parallel of the little a?
That?
Yeah.
Yeah, that's parallel. Over here, there was some indication that K had to be that way, and my question was why?
Because it's a third dimension, so,
Why not that way?
because I said so.
No, not the reason.
Is it always to be facing you?
No. Ava?
Well, I was gonna say it's because of the direction of the torque.
No, but in some way you are closer.
So is it always this way? Are you saying like in every situation, K hat?
What I'm saying is that once I define I hat, J hat, K hat is set. It is not because Stephanie said so. K hat would be out at us. But it's because by default, we are working in a right-handed coordinate system. In a right-handed coordinate system, I cross J equals K.
Is there a reason why it's K and not any other letter?
Typically you go in order. Did you want to do A hat, B hat, C hat?
Not really.
If you did something else, if you just wanted to do like A hat cross Z hat equals Q hat, yeah, you
I
could,
just don't
but
want
that
you
would be
to
very
spring it on me
confusing.
later like, oh, it's K because it's constant.
No, it's K just because it's the next letter in the alphabet. All right, so when you're doing a cross product, the way you pick the direction is the order matters. Commutative property does not hold. You can't flip the order. If you flip the order around, you do not get the same answer. You put your hand in the direction of the first vector. So I wrote is to the right. So I basically have 360 degrees of flexibility in theory, 360 degrees in which I could put my hand. I want it so that when I curl my fingers, not the thumb, when I curl the other fingers, that they move in the fastest direction, or the quickest direction, shortest way to get to the second vector. Since J hat is up, I want to curl my fingers so that they curl up. My thumb points in the direction of the cross product. So I hat cross J hat, I hat cross J hat gives me K hat.
So if it were
So
the, like what would it be if it was the other way? Like
If it's J hat cross I hat,
if,
J hat goes up, I hat's that way, so J hat cross I hat is negative K hat. So if you flip the order around, you get the negative. So J hat cross I hat, negative K hat. Let's talk a little bit about the
Could you draw
spool.
that in isometric view, just for a hot second?
Excuse me?
Could you draw that in isometric view for a hot second?
An isometric view.
Yes.
I'm not quite sure what you mean by that.
Where you can see all three dimensions.
Ah. As best as you can do a three-dimensional drawing.
No, like just coordinate systems.
Oh.
That'll work.
Okay.
could we, so if we did J hat times I hat, could we, so if we get negative K hat, can we define that as positive K hat, or is it like?
Now we're going into a left-handed coordinate system.
So you would have to flip, well, would it still hold?
As long as you were consistent, you should still get the same answer in the end. But by default, you're dealing with the right-handed coordinate system unless you explicitly state. And on the tests, usually on that first page, I say, assume right-handed coordinate system. All right. Okay.
Or lefties.
Yeah, and
Thank you.
pretty much. So in this case right here, if I had R hat up, I have F going that way. So if I do R cross F, my hand goes up, my fingers curl towards F, my thumb points to the back. So that this exerts a torque it exerts a torque that way, which is what we saw. which is what Talon, it wasn't just to be different, Talon knew that it was gonna roll that way. Am I
Because it
correct?
had
Did I
friction.
analyze that right?
I think so, 'cause I think I vaguely remember seeing a demonstration like that before, it's just,
Ah, okay.
so I can't remember.
So
my
you're a
personal experience.
cheater and a liar.
Would, Dr. Fox, would the results of that change if you had a much more friction surface?
More friction?
Yeah. like-
No.
Less friction, yes,
Yeah, it would stay in place if it was frictionless.
it would spin.
Because, let's see, if you,
Can I edit the board a second?
okay,
You're crushing my binder. Nuts.
Oh, yeah, oh my gosh.
Sorry, guys. It's okay. Poor girl.
Thank you. It's outside.
That's isometric view. Otherwise known as what I was taught, Y-symmetric.
okay. I'm less used to seeing it that way, I mean, I have seen it that way, but I'm less used to seeing it that way, so that would be more confusing for me, but obviously, we think differently.
I'm also left-handed, so that helps.
Yeah.
All right, so in this particular case here, in the case of this overhead view of the door, if this is a hinge, I think most of us realize which way that thing's gonna spin. But let's think about it from a math point of view. I have R going that way, F is going up, so I have my hand like this, so in the direction of the first vector, R. I need to curl my fingers so they can go in the direction of the force. My thumb points into the board, which tells me that the torque will be into the board, which tells me that it's gonna rotate that way, which I think we would have done anyway.
So, okay. Okay, two questions. Well, one, how do you know which one comes first?
Which one?
Is it just following that formula, or the R always comes
R is
first?
always first.
Okay.
And R always is like I have, right?
No, R is always whatever direction is specified in the problem.
Could we?
Because it could be like this.
You can make it I had.
But
Yeah.
it starts at the rotational axis and then
Yes.
goes out.
R is always from the axis of rotation to where the force is applied.
So we couldn't switch it in this case. Like we couldn't do it, start at the end of the door and then point toward the hinges. That-
Correct. That would be a different problem.
In the scope of this class, will there ever be more than two forces, or two vectors that we?
I mean, you could easily have multiple forces acting on one object.
Like several.
But that's a
different
net
from there.
force, vector, right? Or is that a net force vector? Or like if you were to have multiple forces acting on the door, then it would be,
There would have to be another force acting somewhere, presumably at the hinge, because otherwise, if it's just, that's the only force, that door would also be moving, have linear acceleration. It would rotate and get faster.
I think my question is, will there ever be another, not force, anything else acting on the system, like finding the torque?
I mean, as in, we've got another force here?
Yeah.
Yes. Oh, yeah.
How does it work when you're finding the torque then? Do you?
The same way, I'd find the torque from this one, I'd find the torque from that one, they happen together.
Okay, so there will never be more than two.
No, there-
Two in finding the torque.
What's the last thing?
It's 15.
There will never be two in finding the torque, you said?
I think she means like, is there gonna be more than two forces?
Yeah, oh yeah. Now, any questions? And I just realized that we were supposed to do a quiz today. Today's the 6th, right?
Yes.
Yeah, I forgot about that.
Two.
Oh, well.
So why don't we take that homework quiz 7 and move that to the 12th, next Tuesday.
Oh, so we'll just take it next Tuesday instead?
Excuse me?
So we'll take it next Tuesday,
Yeah,
and then homework quiz 8 Wednesday, right?
Yeah.
Okay, I just wanna make sure you don't treat me other due dates.
or we could just put 7 and 8 together.
No, please don't do that.
Okay. Was not expecting that kind of reaction. Master said 8 still. It's still due on Tuesday. Sorry about that. If that's gonna mess you up and you need to take it today, then talk to me afterwards. Just a little bit off this morning.
It's the weather.
Understandable,
It's-
actually.
All right. Now, let's go back to our sphere on ramp. As it rolls, what is the pivot point?
The pivot point, where the lines cross.
Where the lines cross.
Like, look at it visually, you see where the extra bold green is?
So where the sphere touches the ramp?
Yes.
Okay. That's the pivot point right there.
It didn't mark.
So if I'm looking at kinetic energy, my kinetic energy about the pivot point is 1/2 I omega squared. My moment of inertia, well, the sphere is no longer rotating, we're claiming that it's not rotating about the center, but rotating about this point right here. So my moment of inertia, I need to use the parallel axis theorem, so I have 1/2 moment of inertia about the center of mass plus the moment of inertia plus m times how far we move the axis, which is just the radius, mr squared times omega squared. Which is 1/2 I sub c, the moment of inertia about the center of mass, omega squared, plus 1/2 m r squared omega squared. Which is 1/2 moment of inertia about the center of rotating about the